Recently, large-scale pre-trained vision and language foundation models have demonstrated remarkable capabilities in many zero-shot downstream tasks. However, it's also been shown that VL models are still brittled in structured VL concepts reasoning, such as the ability to recognize object attributes, states, and inter-object relations. This leads to reasoning mistakes which need to be corrected as they occurred by teaching the VL model the missing skills, often done using private data where the issue was found, leading to a data-free continual vision language learning setting. In this work, we introduced the first continual data-free structured VL learning benchmark and show it is challenging for many existing methods. Therefore, we propose a data-free method comprised of adversarial pseudo-replay as well as a parameter-efficient layered-LoRa neural architecture. Let's take a step back. So we said that vision and language models are brittled in structured concept reasoning. What does that mean? If you look on the right, this is things like attributes. Is a plate sitting on a counter or is a plate pushing on the counter? Or this could also be positions. Is X on top of Y or is Y on top of X? These confuse vision and language models. So we want to be able to teach and correct models for skills such as this, make it experts at some task in a continual learning matter. We don't store private user data, and we don't have access to task IDs during inference. In order to assess the ability to teach these types of models, these concepts, in our work we propose a new continual NLVR benchmark, which we refer to as ConStruct-VL. This benchmark is based off the visual genome and visual attributes datasets, and they use the VL checklist protocol for assessing these benchmarks. So, we found that prompting type approaches, common for continual learning, were too weak for our problem setting. Therefore, we propose to use low-rank LoRa adapters. So LoRa is a fine-tuning adapter where each weight differential from the base model is modeled as a product of two low-rank matrices. This reduces the number of parameters total that have to be trained when fine-tuning, and the results are on par or normally better than vanilla fine-tuning of the model. We mentioned a nice property of LoRa is there's no additional inference latency because all of the learned parameters can be folded back into the original model. We specifically stack layers and propose the Layered-LoRa architecture, or LaLo, where we learned new LoRa's per task. If you see on the right, these indexes refer to the task from continual learning. We learn our delta 1, delta W1 as a product of A1, B1, and then now, when learning task 2, we freeze the delta W1 and now learn a separate parameters of LoRa. One pro for LoRa in continual learning is that we found robust fine-tuning, a key property of LoRa, led naturally to less forgetting. But more importantly, we can store these LoRa in memory for cheap and revisit the past models. When revisiting the past models, we can use this as a form of supervision to regulate the forgetting, which we'll discuss in the next slide. This brings us to our method, the LaLo architecture plus adversarial pseudo-replay. So we're going to start with data from our current task, M2. So we're learning spatial relationships as shown with the image text pair, a handsome dog on a couch. And the past task we learned was the color task. So first we're going to simply learn the new task with cross-entropy loss on the spatial relations data. As mentioned in the past slide, we don't directly fine-tune the model. Instead, we use layered-LoRa. In this example, the frozen backbone weights are all locked. The past LoRa from task 1 is frozen and locked, and we're only learning the new LoRas. So the key question is, when learning task 2, how do we inject and regularize the knowledge that we learned in task 1? What we're going to do is we're going to leverage adversarial pseudo-replay. Specifically, using our new task data, we're going to generate negative examples to the past task model conditioned on the current batch data. If you see here, we do some adversarial steps and we optimize the text pair associated with a handsome dog on a couch to now be an adversarial match and label to the color task. So you see now instead of a handsome dog on a couch, we have an adversarial text example learned, a pink dog on a couch, which is clearly wrong. So why negative? It's much easier to generate negatives versus positives. We can have a lot more confidence that we are getting correct data because the space of negative examples is much, much larger than positive examples. So what do we do with this negative adversarial example? We use it for a distillation where we're able to distill the margin of the adversarial examples from our past task model M1 into our current task model M2. So how do we perform in the ConStruct-VL benchmark? Well, we implemented many different continual learning methods for our studying. We found that learning without forgetting, our prediction distillation method, performed the best. Surprisingly, the continual prompting methods such as L2P and dual prompt had very low performance, which we found to be very strange. But most important, we found our method had by far the strongest performance on this benchmark. So the takeaway here is that the layer-LoRA approach plus adversarial pseudo-rehearsal is a good approach for continual vision language learning. We have many more experiments, results, and analysis, including 3 benchmarks total, ablation results for every decision, and our full paper. So we invite you to please check it out. We will show one analysis here though. How do we compare it to replay? As a reminder, we advertise our method as a replay-free approach. And on 3 different benchmarks, we found that our method was either competitive with or on the same performance as replay. We see here specifically that for 2 of these benchmarks, it takes significant replay data to match our performance. And on one of the benchmarks, we matched performance of replay no matter how much we increase the replay amount. So the takeaway here is that our method is competitive with replay, but for the most part, we found that replay will always help. Thank you for listening to this talk. Please come by and visit our poster at CVPR. You can also check our main text app by following the QR code link below to read more details. Thank you again for watching.